Welcome back to part 2 of lecture 16 in week 9. So in this part of the lecture, we're going to see yet another stability criterion for the closed loop control systems. And this is called the Nyquist criterion. So the Nyquist criterion per se is quite easy to implement. You really have just to count circles and count poles. That's all you need to do. So when it comes to the actual criterion, it is probably the easiest of them all. However, in order to get there, well, the road might be a little bit winding. In other words, it's usually more difficult, the explanation of the criterion rather than the criterion itself. So I hope I'm going to make it easy. I try to, or easy enough. I try to do so in the notes. So if you don't understand, again, reach out to me, because once you understand it, it's really straightforward. Many times people have troubles with the Nyquist criterion simply because they haven't been taught the criterion well enough. So, I'll kind of take the blame if you don't understand, but please do your best to follow. Okay, so here, as usual, we're going to take a look. We're going to consider our unity feedback control system with our plant and our generic controller. So GC and G combined together, we've been calling them LOS, the loop transfer function. Of course, if we take in consideration the overall thing, that we have the closed loop transfer function T of S. So just a quick summary of what we've seen so far in terms of stability criteria. We saw the Roth-Hurwitz criterion. All you need to have is the characteristic polynomials, and then you just play with the coefficients, find the Roth array, and check the sign. So just a few calculations, but quite straightforward. Then we have, the brute force method, compute the poles of the closed loop transfer function itself, and just check the real parts. If all the real parts are negative, then you have a stable system. This is also quite easy. And then you can infer some information about the stability. If you have a parameter, let's say a constant gain, then you can vary, or any other parameter, and you can write the characteristic equation as 1 plus k L of s equals 0. You can also draw the root locus and infer some stability information from it. Now, today, we're gonna take a look at the last, which is the Nyquist criterion. And this is a mix of a computational / graphical methodology. So we're going to take a look at a certain plot, which is going to be called a Nyquist plot. Good news is that you don't have to learn how to draw it. It will require quite some time, and I think it's not really, in the end, that useful. We have enough with the root locus and the Bode plots. You have enough to draw already. So, the Nyquist plot, we'll just generate them using MATLAB. So it's just a little bit of magic there. It's not really magic. There are actually ways of learning how to draw them. And in your textbook, there's also a quite good explanations, or you can find endless videos online about that. But again, we have a limited amount of time, and just drawing of the Nyquist plot alone would take at least a complete lecture, if not 2. So I think it's not really worth it, because the criterion itself, how to use and interpret the plots in order to assess stability, is more important from my point of view. And moreover, not only will we be able to assess the stability of the closed loop system by looking at these magical Nyquist plots, but as we will see next time, though, we can also see from the plot itself the stability margins. Same thing that we already saw with the body plot, but we can also infer the stability margins just looking at the Nyquist plot, which is just one and not two like the body plots. And also we'll get some extra information about the so-called sensitivity, but this is going to be the topic for the last lecture. All right, so let's try to get there. So in order to do so, let's consider three transfer functions. Two, we're already very familiar with. So one is just our loop transfer function, L of S. Then we have T, which is our closed loop transfer function. And then we're gonna use an auxiliary transfer function, which is just L of S plus one. We're gonna call it just auxiliary transfer function. I believe your textbook calls it F of S, but we'll just leave it L of S plus one because that is what it is in the end. I don't want to introduce more notation. All right, so let's just take a look at these three transfer functions. So L of S, as we've already established, is just GC times G. And let's say that we can write it as a fraction with a numerator and a denominator. So N of S over D of S, usual stuff. So if you wanted to find the zeros of L of S, what do you have to do? You have to solve N of S equals 0, and the solutions to these equations are the zeros. What about the poles? Well, the poles are the solutions of D of S equals 0. Again, nothing new so far, but it's good to review things. Now let's take a look at the closed loop transfer function T of S. How do we compute that? Well, that is L of S over 1 plus L of S. Of course, according to the geometry of this block diagram. It's a standard one. So L of S over 1 plus L of S. Now, using the fact that L of S is N over D, let's rearrange things slightly. And so we see that T of S can be written as N of S over N of S plus D of S. So what are the zeros of the closed loop transfer function? Once again, they are the solutions of the numerator. So it's N of S equals 0. So you already see that the zeros of the loop and the closed loop transfer functions are the same because they are both the solutions to the same equation. What about the poles of the closed loop transfer function? Well, we have to solve the denominator. So N of S plus D of S equals 0. And that's what we're really interested in because it's the poles of the closed loop transfer function that contain all the information about the stability. But as usual, we're trying to gather information about the closed loop transfer function without having to actually compute the poles because in our examples we have at max we've seen 3 poles, 4 poles, but you can have systems with many more. And so if you have to do things by hand, it becomes almost impossible. And remember that all these methodologies were introduced and thought when the computers weren't really available or powerful at all. So you had to use other strategies. Anyway, now let's take a look at the third transfer function, that is the auxiliary transfer function, as L of S plus 1, which you might already see that L of S plus 1 is the denominator of the closed loop transfer function. So L of S plus 1 is N over D plus 1. Plus 1, so rearranging this, we have N of S plus D of S over d of s. So what are the zeros of L of s plus 1? Well, they are the solutions of n of s plus d of s equals 0. And the poles of this auxiliary transfer function are simply the solutions of d of s equals 0. So you see here that we really have only 3 equations, and the solutions to these 3 equations provide the information of either zeros or poles of each of these 3 transfer functions. So we've already established that the zeros of L of s are equal to the zeros of T of s. That's good, but this piece of information is actually useless in terms of what we are going to develop. So it's just there, but we're not going to do anything about it. Now let's take a look at something more interesting, and we're going to see why in a few minutes. Well, let's find the other pairs. So we see that the poles of L of s, that is d of s equals 0, are equal to the poles of L of s plus 1. So you take L of s, even if you add a constant, you add 1, the poles of these 2 transfer functions are the same. That's not really obvious, is it? But that's the truth. So we have that the poles of L of s are equal to the poles of L of s plus 1. This is going to be clear a little bit later, but don't forget about this second piece of information. Thirdly, we have that the poles of the closed loop transfer function, n of s plus d of s equals 0, are equal to the zeros of the auxiliary transfer function, L of s plus 1. Same equation. So why is this important? Well, because once again, we're trying to get all the information about T of s that we can by just using what we know, that is L of s. That's usually what we know. You know your plant, G, and you know your controller or your compensator because you are designing it. So you know the information about it. So you know GC. Knowing both GC and G, you know, therefore L. You know exactly where the zeros and the poles of L are. So if we can get the information that we have about L of s and infer something about the closed loop transfer function that is T of s, that's golden. That's what we want to do. So now we've already seen that, okay, if we just add 1 to our loop transfer function, that is if we have L of s, its zeros are equal to the poles of the closed loop transfer function. So the stability info that you get from the zeros of L of s plus 1 is the same information in terms of the stability of the closed loop transfer function, that is the poles of T of s. Now, in this example that I'm going to show you, that just simply looking at the poles of L of s and T of s, well, they are not really related, at least graphically. So you cannot really infer anything about the poles of T just looking at the poles of L. Let's see the example. So we have this L of s as s cubed plus 3s squared plus 5s plus 7 over 2s to the power of 4 plus 4s cubed plus 6s squared plus 8s plus 2. So we have 3 zeros of L of s, but again, the zeros of L of s are irrelevant, and then 4 poles of L of s. And normally you would know them, so you would probably have L of s as factorized already. So what is T of S, the closed loop transfer function? Easy to compute. I'm just going to go a little fast here because this is not really the objective of this lecture. You should already know how to do this step. If not, make sure you do. And you still don't know how to do it, just let me know. Now, let's try to plot the zeros and the poles of L and of T of S. And let's see if we can find any resemblance, any similarities, at least from the graphical point of view, between the poles of the two transfer functions. So here in blue, we have the poles of L. So we have 1 and 2 real poles and 1 and 2 complex conjugate poles. Now closing the loop, you see that these poles get to another couple of complex conjugate poles. And there's not really an obvious way of how the first 4 transform into the latter 4. It's really not obvious. So we cannot really use just the poles of L of S to get information about the poles of T of S, unfortunately. On the other hand, you see that the 3 zeros here circled, they are the same for L and for T, but unfortunately, they're not going to help. So is there something else that we can use in order to relate L of S with T of S? And the answer is yes. And the answer is the Nyquist plot. Now, never mind how we get the Nyquist plot. I just want you to see that the Nyquist plot of L of S for that particular example is this blue line once again. And the Nyquist plot for the auxiliary transfer function L of S plus 1, remember the zeros of L of S plus 1 coincide with the poles of T, so they are connected. But you see that Nyquist plot wise, the two Nyquist plot have the identical same Mickey Mouse shape, rotated by 90 degrees. But an important thing is that they are only translated by 1. So if you take any point on L of S Nyquist plot and you shift it in the x direction by 1, by plus 1, you get the point on the L of S plus 1 Nyquist plot. You can take any point, for instance, here. So you see that it's just a simple translation of these two, of the original shape into the new plot. So you'll see that now we can actually relate L of S and L of S plus 1 using this tool. Again, for now, let's forget about how we got it and let's analyze why it is important and how it is generated and why we can use it in order to determine the closed loop stability. And then later on, as I said, we can also use it in order to assess stability margins and system sensitivity. In order to get to the Nyquist plot and then eventually to the assessment of the closed loop stability, we have to start a little bit back, and that is from the concept of contours mapping. Sounds weird. What is that? Well, a contour map is just a contour or trajectory that is being mapped from one complex plane to another complex plane using a map. All right, it seems that I'm going around same concept without saying anything. So let's take a look at an example to better understand what I mean. So we need a map, and I'm gonna tell you that this is a map. F of s equals 2s plus 1 is a map. Hold on a second, that looks like just a function in the S domain or a transfer function. Well, as I pointed out here, you can interpret f of s as all three of these things. It is true that it is a function in the S domain. It is also a transfer function if you want to perceive it from that perspective, but it is also a map. So let's exploit f of s as a map. So as I said, what we're going to do, we're going to start from a line, a closed line in a complex plane, and that's exactly what we're going to do. Let's take just the square line. And we're going to use f of s to transform or to map this contour into a new contour in another complex plane. So starting from the complex plane to the left, well, that is our usual S equals sigma plus I omega. So our real axis is sigma and our imaginary or y-axis is omega. And also what we want to do is we give a direction of circulation for this contour. So we're gonna go around this line in, let's say, a clockwise direction. So here, for simplicity, I drew it as a square. So what we can do is that we can map the vertices of the square and see where they end up being once we map them with the f of s equals 2 of s plus 1. So what does that mean? It means we have to find new coordinates. It's easier to see than to explain, perhaps. So f of s is 2s plus 1, but s is sigma plus I omega. So let's just substitute that. So we have 2 that multiplies sigma plus I omega plus 1. And so now we have 2 sigma plus 1 plus I times 2 omega. So our new real part is 2 sigma plus 1, and the new imaginary part is 2 omega. So if we call our new coordinates, instead of sigma and omega, we call them u and v, we can form another complex plane. Instead of calling it the S plane, I'm going to call it the f of s plane because it's the complex plane that is obtained through the map f of s. And so the coordinates, the axes are u and v. So let's start by mapping the 4 vertices. So the transformation from the old to the new coordinate is that the new coordinate u is 2 times sigma plus 1 and v is equal to 2 omega. Again, this is not a general rule. This is just a specific coordinate change due to the specific map. So now if we use 1, 1, for instance, so sigma is 1 and omega is 1, then u is 2 times 1, 2, plus 1, 3. And then v is going to be 2 times 1, so 2. So 1, 1 is mapped into 3, 2. So this point here, this is mapped into this. Now let's follow the contour in the S plane clockwise until we hit another vertex. So in this case, we have 1, minus 1, and that is mapped into 3 minus 2. And so we have over here 3 minus 2. So this vertex is mapped right here. And then we can do the same for -1, -1, and -1, +1. And we find -1, -2, and then -1 plus 2. There we go. So you see that we've obtained a new contour, a new plot in another plane. And let's see, have we maintained the direction of circulation? Well, we went from 1, 1 to 1 minus 1 clockwise, and we found first 3, 2, and then 3 minus 2. So yes, we've maintained the direction of circulation, but you see that we've obtained a new figure. It's still a square, but now it's different. It's the side is longer and it's not centered at the origin. So normally, if you use a certain map, f of s map, well, you're gonna with a contour, that is up to you which contour to find. Then you're gonna find a different contour. So if we had chosen an initial contour as a wiggly line like this, as long as it's close, we would have probably found another wiggly line in the f of s complex plane. One thing that I forgot to do is just to place, and then we will see why this is important, on the original S plane, the poles and the zeros of our map. So now let's treat our map as a transfer function. So let's find its zeros and poles. Well, f of s, if it is equal to 2s plus 1, it has only 1, 0 really at -1/2. And so we can easily place it right here. Now let's draw a few considerations based on this specific example. And let's see if we can generalize these considerations, if we can find a way to generalize and find a rule. So for this example, we saw that we started with an S contour that is closed, the original purple square, and we ended up with a closed contour in the f of s plane. Here I'm using this capital gamma to indicate the contour. Sometimes that's what's used. So capital gamma of s is just a contour in the f of s plane. So this is a general rule. If you start with the closed contour in the s plane, you're going to find a closed contour in the f of s plane. That's it. That's always true, always valid. And so keep that in mind. Another thing that we've noticed is that the direction of rotation is maintained. But this is valid just for this example. This is not valid in general. The direction of circulation might change. So if we started clockwise in the S plane, we might end up with a contour in the f of s plane that has a different circulation direction, could be counterclockwise. So that is not always true, but for this example, the rotation, the direction of the rotation is maintained. Then another thing that we can notice, and we will see that will be useful later, is that the S contour encircles, means goes around, 1, 0 of f of s in the clockwise direction. What does that mean? It means that we have a 0 at -1/2, and we chose the contour to encircle such 0. And how many times does it encircle? Just once. So if you start from one vertex and you follow all the contour and go back to the same vertex, you've just gone around the 0 once. Again, this is not always the case, because if we had chosen a different contour, always closed, let's say we had chosen this one, well, this wouldn't have encircled the 0 of f of s at all. So this consideration, once again, are specific for the example, but they're going to be useful in a few moments. Now let's take a look at the f of s contour. And we notice that it encircles, so it goes around the origin once, always in the clockwise direction. Okay, very good. So let's take note of that. Just one quick annotation about the notation is that we're going to consider positive encirclements the ones that are taken clockwise. So the clockwise direction is positive, whereas the counterclockwise direction is negative. Okay, so we've drawn some considerations with this particular example. Let's try now to generalize it. And the generalization comes with the name of a theorem. It's called Cauchy's theorem. We're not going to prove it, we're going to just state it. And the theorem says that if a closed contour in the S-plane, the purple one, encircles Z number of zeros and P number of poles of f of s, in our case, we had 1 0 of f of s that was encircled and no poles of f of s, and the direction of the encirclement is taken clockwise. Okay, we did that along the contour. Then, and we're gonna now get some information about the mapped contour. Now, the corresponding contour in the f of s plane will encircle the origin, that is the point 0, 0 of the f of s plane, obviously, n times. And n is given by z minus p. All right, so this is a powerful statement. This is a powerful conclusion. Again, I'm not going to prove it, but trust me, this is true. So this says that if we pick a contour in the S-plane, and let's always pick it so that the direction of rotation is clockwise. Depending on how many zeros and or poles of the transfer function that functions as a map we encircle, then we're going to know how many times the origin of the transformed complex plane will be encircled, and also in which direction. Let's try to apply this to our example. So in our example, we had f of x equals 2s plus 1. And based on the contour that we arbitrarily chose, again, the contour that you're choosing here in the S-plane, it's up to you. The only thing that I said, just choose it closed. And now the other thing in the clockwise direction. But other than that, then the shape is really arbitrary, and the location also. So in this case, we have that the S contour encircles 1 0 of f of s. F of s doesn't have any other zeros or any other poles, so it encloses everything of f of s. So z is equal to 1. z equals 1 doesn't mean that f of s has 1, 0. It means that the contour that you chose in the S-plane contains 1, 0 of f of s. F of s might have 100 zeros, but if you only encircle one of them, then z is equal to 1. How many poles of f of s are within the encirclement, within the contour that we chose? None. Also because f of s doesn't have any poles, but that is not really the point here. So we have that capital Z is equal to 1 and capital P is equal to 0. So due to the Cauchy's theorem, we have that N is equal to Z minus P, which is 1 minus 0, which is 1. What does that mean? It means that the origin of the transformed complex plane, the f of s plane, is encircled one time. In which direction? Remember the notation. Positive means it means clockwise. Negative means counterclockwise. Here we have +1. So it means that the origin is encircled one time clockwise. Let's go and check. Was that the truth? Yes, we have the origin that is encircled once clockwise. Let's take a look at a couple of examples to really fix the concept. But before doing that, one trick that I want to teach you is how to actually count the number of encirclements. It might sound easy, or at least it was for the example that we saw, but let's say, what if we had a contour like this, and I'm asking you, well, how many times is the origin encircled? Keep in mind that you can count the encirclements with respect to any point that you want. But for now, for simplicity, let's just refer to the origin. So what you can do is just draw a line starting from the point around which you want to count the encirclements. So the origin in this case, just draw a straight line in any direction. Let's do in this direction, for instance. Now count all the intersections with the contour. In this case, we have 2 intersections. And put yourself on the line. So from the origin, in this case, move away and see how the plot crosses your way when you intersect it. So at the first intersection, the curve intersects from right to left in a sort of a counterclockwise. So from right to left is going to be minus. So here we have -1. And then at the other intersection, we have that the direction is coming from left and is crossing towards your right. And so we have +1. So the total amount of encirclements, -1 + 1, is equal to 0. So the total encirclements of the origin is equal to 0. You don't believe me? Let's take another line. Let's cross the plot more times. Let's do it like this. Okay, let's hop on the line and let's go. First intersection. The contour is crossing our path from our relative right to left, so it's a -1. Then we have another intersection here, and the path still crossing our way from right to left, so another -1. Then what about this intersection? Now we're crossed from left to right, so it's +1. And the final one is also from left to right. So it's another +1. So you see that -1, -1, +1. plus 1 is still 0. So it doesn't really matter which line you're choosing. If you do so, you're always going to find 0 for this case. It means that the origin is encircled only 0 times, so none. Although it appears that it is encircled, but one encirclement cancels out with the other one because one is in the clockwise direction and the other one is in the counterclockwise direction. So overall, there's no encirclement of the origin. So this trick is very useful, I believe. All right, with that being said, let's take a look at a couple of examples in order to apply the Cauchy theorem. So let's say that now we have a map that has a bunch of zeros and poles. Let's say that we have zeros here, then here, and a couple of more here. Then we have a pole right here, a couple of poles right here, and another pole. So overall, 4 poles and 6 zeros. Now let's choose a closed contour. Remember, we only need it to be closed and has to be clockwise. Then it's arbitrary. So let's just take it like this. So can we predict how many times the origin in the f of s plane is going to be encircled? Of course we can. All we need to do is to count the number of zeros and the number of poles that are within the S contour. So how many zeros are within the contour? We have 1, 2, 3, and 4. So z is equal to 4. Once again, pay attention. Z is not the total number of zeros because the total number of zeros is 6, but only 4 of them are enclosed. So Z is equal to 4. What about P? How many poles are within the contour? 1 and 2. So P is equal to 2. Therefore, according to the Cauchy's theorem, we have that the encirclements of the origin of the f of s plane is equal to z minus p, which is 4 minus 2 equals 2, which is greater than 0. It means that the origin is going to be encircled twice in the clockwise direction. Now, I don't know exactly how the actual contour in the f of s plane will look like. It just qualitatively speaking, is probably, it can look something like this. We have the origin encircled twice. How is it twice? Again, let's draw a line. Intersection 1, we have from left to right, so it's a +1. The other intersection still from left to right, another +1. So we have +2. 2 counterclockwise encirclements of the origin. We'll get to the stability. It's just, it takes a little bit of time, and I prefer to just break down things into easy steps. All right, let's take a look at the same example. So same map, that is, it has the same poles and zeros, but this time let's choose another contour. In this case, let's choose a contour like this, close clockwise. How many zeros are we encircling? 2, 1 and 2, so z is equal to 2. How many poles? We have 1, 2, and 3, so p is equal to 3. Therefore, how many times will we encircle the origin in the transformed plane? 2 minus 3 is equal to -1, which is negative. So we're going to encircle the origin 1 time counterclockwise. There we go. So this is the application of the Cauchy's theorem. Quite easy, right? Now, how can we use the information that we know, that is the results of the Cauchy's theorem? How can we use that in order to find the stability of a closed loop system? Well, first of all, recall what I said in the beginning. That is, the poles of T of S are equal to the zeros of L of S plus 1. So in order for the closed loop system to be stable, we don't want any poles in the right-hand side of the complex plane, right? Remember that. That's just a classic stability criterion. We don't want poles right here in the right-hand side of the plane, because that will cause the system to be unstable. Now, I'm not going to talk about poles of T of S anymore, because we've established that they are the same as the zeros of L of S plus 1. So there's a reason why we're using L of S plus 1. So now, instead of talking about poles of T of S, I'm going to talk about zeros of L of S plus 1. So same stability criterion says, in order for a system to be stable, we don't want zeros of L of S plus 1 in the right-hand side of the S plane. Same thing. So how can we make sure that we don't have zeros of L of S plus 1 in the right-hand side of the S plane? Well, why don't we map? Why don't we encircle? Why don't we take a contour in the S plane that takes care of all the right-hand side of the plane? Why not? That's exactly what we're going to do. This is it. We're going to take this contour. So here it's obviously, it's an infinite contour, but it has to be closed. So it's going to close at infinity. So what we're going to do is we're going to start from the origin. We go all the way up to infinity, and then we come down with a semicircle, and then we come back from minus infinity and close. So it's technically infinite, but we can build it so that it's a closed, you have to think about it as a closed semicircle whose radius approaches infinity. So this way, we are taking care of all the points on the right-hand side of the plane. So if we map that, we know that once we have the mapped contour, we can count the encirclements of the origin of the mapped plane. That is n, but n is z minus p. So by just looking at the encirclement of the origin in the mapped plane, we have something. We have information about the difference between the zeros and the poles of L of S plus 1 that lie on the right-hand side of the S plane. Yes, but we are interested in the zeros of L of S plus 1. Now we only have the difference between the zeros and the poles. What's wrong with that? Well, we would know about the zeros, how many zeros lie on the right-hand side of the plane, only if we knew about the poles, because now we only know the difference between them. If we go back to the examples here, we have encircled in this example 4 zeros and 2 poles. So we only know that we have 2 extra zeros and poles. But if we just look at the f of s plane, so let's say we don't know what was going on in the s plane, and let's say we only look at the f of s plane and the mapped contour, Well, we can count, okay, it encircles the origin twice clockwise, very well. It just means that originally we drew a contour plot that contains 2 more zeros than poles, but it could have been 5 zeros and 3 poles, 2 zeros and 0 poles. In this case, it was 4 zeros and 2 poles, but we only know the difference really if we take a look at the mapped contour. Same thing with the second example. We have one counterclockwise encirclement of the origin. It means that whatever we chose as our S contour contain one more pole than 0. But there might have not been zeros at all. It could have been just one pole and 0, 0. You still have 0 minus 1 equals to -1. So just counting the encirclements of the contour in the f of s plane, in the map plane, does not tell you how many zeros you have encircled. It tells you just the difference between the zeros and the poles that you've encircled. For instance, in this plot that I chose, I drew it so that, and now let's just call it Nyquist plot, because when you start with the S contour that is all the right hand side of the plane, then whatever you get is called the Nyquist plot. So here we're encircling the origin once counterclockwise. Okay. N is equal to -1. So it means that Z minus P is equal to -1, or that Z is equal to P minus 1. All right. But is Z 0 or is Z positive? Because the closed loop system is going to be stable if and only if Z is equal to 0. If Z is equal to 0, it means that there are no zeros of L of S plus 1 in the right-hand side of the plane. Remember what I told you? I'm not going to talk about poles of T of S anymore because zeros of L of S plus 1 are the same as the poles of T of S. If we have Z greater than 0, then the closed loop system is unstable because we have at least 1 0 of L of S plus 1 in the right-hand side of the complex plane. And being the zeros of L of S plus 1 equal to the poles of T of S, there we go. All right, going on with this example. If, let's say that Z is equal to 0, that would imply that P minus 1 was equal to 0. That is, P is equal to 1. What if Z is greater than 0? Then P minus 1 is greater than 0. That implies that P is greater than 1. Also here, another piece of information that you have is that you cannot have P equals 0. Because if you had P equals 0, then Z would be negative, and that cannot be the case. So now the last ingredient for us to determine the stability of the closed loop system is to figure out how many poles of L of S plus 1 are on the right-hand side of the plane. You say, okay, but how many things do we have to know something? But the poles of L of S plus 1, go back to the beginning of this part 2 of the lecture. Weren't they the same as the poles of L of S? They are. And why is this important? Because we know everything about L of S. We know exactly where all the poles are. So if we know where the poles of L of S are, we automatically know where the poles of L of S plus 1 are. And so we just have to count how many of them are in the right-hand side of the complex plane. That is, count how many of them have positive real parts. And so we have P, we have capital P. We can count it. Once we can count P, and then we count the encirclements using the Nyquist plot that magically appeared because of MATLAB, but that's another story, we can determine Z. And if Z is equal to 0, closed system is stable. If Z is greater than 0, closed system is unstable. That is your Nyquist stability criteria. There's just one more thing, and that's actually something to simplify our lives. Remember the relationship between the Nyquist plot of L of S and L of S plus 1? The Mickey Mouse head plots? Where are they? There we go. You see that they are the same, just shifted. Now we've been talking about L of S plus 1, L of S plus 1, and its Nyquist plot. But why don't we take a look at just the Nyquist plot of L of S? That's what we have in the end. That's what we start from, L of S. So here, pretty much, we're just going to the left. We're just subtracting 1. So instead of counting the encirclements of the origin, there you go. Instead of counting the encirclements of the origin for the L of S plus 1 Nyquist plot, we can count the encirclement of -1 for the L of S Nyquist plot. And that's it. So, in summary, what do we need to do? We have our loop transfer function L of S. We find a way to generate its Nyquist plot. Normally, you will learn how to draw it. I'll spare you that. So we'll use MATLAB to generate the Nyquist plot. Good. Now, count the number of encirclements of, now not the origin anymore, because you have to translate, we had to translate everything to the left. So count the number of encirclements of -1, 0. And so you've determined your N. Because again, the two Nyquist plots are the same. They're just shifted by a unit. So N remains the same. Instead of counting the encirclements of the origin, you count the encirclements of -1, -1, 0. So it's the real -1. All right, so we have N. Now, if you count the poles of L of S in the right-hand side of the S plane, that is the poles with positive real parts, you have P. And due to the Cauchy's theorem, we have that Z is equal to N plus P. So that is the number of zeros of L of S plus 1 that are in the right-hand side of the S plane are equal to N plus P. And your system is stable if Z is equal to 0, and unstable if Z is positive. That's it. That's the Nyquist criterion. So all you need to do is count and sum the two numbers. Very, very easy in the end. You see that it took us a little bit to get there. There's quite of a reasoning behind it. It's very fascinating. But the criterion itself is straightforward. Just count the encirclements of -1. Use the trick that I taught you. Count the poles of L of S, which are the same as the pole of L of S plus 1, with positive real parts. Sum N and P together, and you have Z. If Z is 0, good. Closed system is stable. If Z is positive, closed loop system is unstable. And so here is just a more formal definition, more proper definition of the Nyquist criterion, it says, but if you've understood, again, you might have to watch it another time and think about it, but it says that a feedback control system is stable, in other words, T of S, if the contour plot in the L of S plane encircles counterclockwise the -1,0 point as many times as the poles of L of S with positive real parts. It says that Z is equal to 0, that is a closed loop system is stable, if and only if N is equal to minus B. So the number of encirclements of the -1,0 point are equal to minus P. So counterclockwise number of the poles of L of S with positive real parts. Let's just take a look at a couple of examples. All right. L of S, S plus 2 times S plus 10 over S minus 1 times S plus 3 minus 4i times S plus 3 plus 4i. Let's count the poles first. What are the poles of L of S? Well, we have 3 of them. One is plus 1, and then the other 2 are minus 3 plus or minus 4i. P is equal to, well, P is the number of poles with positive real parts, 1. Now, we've generated a Nyquist plot right here. It's kind of a Pac-Man ghost. How many times are we encircling the -1,0 point? Where is the -1,0 point? Here. 0 times. We're not encircling it at all. So N is equal to 0. Nyquist criterion says that Z is equal to N plus P, which is equal to 0 plus 1 equals 1, which is greater than 0. It means that we have a 0 of L of S plus 1 or a pole of T of S in the right-hand side of the S plane, which means that the closed loop system is unstable. You don't trust me? Let's compute the closed loop poles. First 2 are minus 3.08 plus or minus 4.74i. Third one is plus 0.156. Aha. Positive real part. Closed loop system is unstable. Let's take a look at second last example. L of S and 9 over S minus 1 times S plus 2 times S plus 3. What are the poles? Plus 1, minus 2, minus 3. P is equal to 1. We only have one positive pole. All right. Nyquist plot, 8 figure. How many times are we encircling the -1,0 point, and which way, clockwise or counterclockwise? Let's just take one line. Here we're crossing from right to left, so it's -1. And that's it. So N is equal to -1. Stability criterion from Nyquist says Z equal to N plus P is equal to -1 plus 1 equals 0. Z equals 0. Closed loop system is stable. Let's double check. Computing, again, this computation, I'll do it obviously through MATLAB. The poles of the closed loop system, we have one at -3.94 and the other two are -0.03 plus or minus 0.87 I. All 3 of them have negative real parts. System is stable. That's it. All right. That's it for today. Hope you enjoyed this. And I hope you understood it. If not, my fault. No, I'm just kidding. It's your fault too. I'll see you next time and take care.